math, it's all about math, the wonderful world of math. Welcome to the wonderful world of math. Today we're going to continue our adventure with the half-angle trigonometric identities. So let's remind ourselves, here are our half-angle identities for sine and cosine, the big ones, the important ones. What we're going to do today is we're going to talk about how to find the sine of half of an angle given not the original angle, but just the sine or cosine, or even tangent, or whatever, one of the 6 trig functions of the original angle A. So as promised, here's the question. If sine of A is negative 8 over 17, and notice I did not say A equals negative 8 over 17. I have not told you what A is. I told you what the sine value at A is. Sine of A equals, not A equals, sine of A equals. And here I've told you that A is in the 3rd quadrant. I haven't said what A is, but we know that it's in the 3rd quadrant. And now I've asked you to find sine of half of A, and cosine of half of A, and tangent of half of A. So if I'm asking for sine of A over 2, you might think that it's important that we have half-angle identities. A over 2. So let's start with sine of A over 2, right? The half-angle identity says that this is plus or minus the square root of 1 minus cosine of A all over 2 inside the square root. Now, we don't know what A is, so we don't know what A over 2 is. But we should be able to figure out whether this is plus or minus, that's important, and we should be able to figure out what cosine is. Now, I did not tell you what cosine A is, but I did tell you what sine of A is. We have identities that allow us to relate sine and cosine. Which identities relate sine and cosine and nobody else? If you said sine theta equals cosine of pi halves minus theta, a cofunction identity, either of them really, this isn't quite what we wanted, because you'll notice that these angles aren't the same. That's kind of the point of the cofunction identity. These angles are complements, but these angles, these angles are supposed to be exactly the same. It says A and A. So this one's not going to work. If you said sine theta over cosine theta equals tangent theta, this one doesn't work either. We wanted an identity that only related these 2 functions. This has a 3rd function in it, so that's not going to work either. So hopefully we found the fundamental identity. Sine squared theta plus cosine squared theta equals 1. It relates sine and cosine and nobody else. So we know that sine squared of A plus cosine squared of A has got to equal 1, but we also know what sine of A is. So instead of saying sine squared A, sine A squared, right, we can say negative 8 over 17 squared. Because sine of A is negative 8 over 17. If it makes it easier for you, you can think sine squared of A is sine of A parentheses squared, and that the stuff in the parentheses is this guy. So that's how we get negative 8 over 17 parentheses squared plus cosine squared of A equals 1. This is something that we can simplify. 8 times 8, and negative times negative, 64 over 289, plus cosine squared A equals 1, subtracting this from both sides, so that we get cosine squared A by itself. Cosine squared A is equal to 1 minus 64 over 289. Get a common denominator, right? 289 over 289 minus 64 over 289. Because they have a common denominator, I can move the subtraction up to the numerator. That's the whole nice thing about subtracting like fractions. And then we subtract the 2 terms in the numerator, we get 225 over 289. This is cosine squared of A. So what is cosine of A? Well, you take the square root of both sides to get rid of that square. take the square root of cosine squared, you get cosine of A. To take the square root of the left-hand side, you take the right-hand side, you do the top and the bottom separately. 15 over 17, right? Wrong. You gotta stay plus or minus, man. Plus or minus. What quadrant are we in? We're in quadrant 3. This is important. This is the first time, but not the last time, this will be used. This is telling us quadrant 3, so cosine must be negative. Cosine is negative in the third quadrant. So we've got that, which means, finally, I know what to put here. I had to use the Pythagorean identity, and two pieces of given information, this one and this one, to figure out what goes here. But now I can do it. And the other thing I have to choose is this. So we know what goes here, but whether I have plus or minus here depends on theta, or alpha in this case. To figure out whether this should be plus or minus, I need to know what quadrant A over 2 is in. But I only have this information about A. So what we do is we take this inequality about A and turn it into an inequality about A over 2 using algebra. I know that if I have an inequality like this, I can multiply both sides by the same thing, as long as it's not zero. And if that thing is positive, then the inequalities are preserved and everything is equivalent. So I'm going to multiply both sides by 1/2. A times 1/2 is going to be A over 2. And pi times 1/2 and 3 pi over 2 times 1/2. And we simplify those things. Pi, you know, has an invisible denominator of 1, in case you were worried. So pi times 1 over 1 times 2. Top times top over bottom times bottom. A times 1/2, like we said, is A over 2. And 3 pi over 2 times 1 over 2. Again, top times top over bottom times bottom. What quadrant is this in? It's bigger than pi over 2, but it's less than 3 pi over 4. So that's on the unit circle. Between here and here, you're somewhere in here. This is quadrant 2. It's not the entirety of quadrant 2, but it is definitely in quadrant 2. So if this angle is in quadrant 2, is the sine of this angle positive or negative? If you said sine is positive in quadrant 2, you are correct. So finally we know we want the positive square root of 1 minus, what was cosine of A? Cosine of A was negative 15 over 17. So we've got negative 15 over 17. And we've got to simplify that. So the first thing is this double negative. 1 minus a negative means 1 plus 15 over 17. And then, like before, the strategy is to get a common denominator. 1 is equivalent to 17 over 17. Combine the two terms up top, 15 plus 17. And then simplify the compound fraction by multiplying by the reciprocal of the denominator. The reciprocal of 2 is 1/2. Now, instead of multiplying the top times top and the bottom times bottom, look for common factors between the top and the bottom first. These both have a common factor of 2. So this reduces to 16 over 17. 16 over 17 is not really a rational number. But the numerator does have a nice square root, so you do it separately. The square root of 16 over the square root of 17. And if it makes you feel good to rationalize the denominator, go right ahead. That means that to get the denominator to be a rational number, you multiply the top and the bottom by the radical expression in the denominator here. Root 17 times root 17. Any radical expression times itself. It's just the inside. So your answer can look like this, or like this, and they're both pretty fine for us. So coming back to our original problem, we have found one of the three answers we were asked for. We found sine of A over 2. Let's find cosine of A over 2. Cosine of A over 2 means we're going to use the cosine half angle identity. plus or minus the square root of 1 plus cosine of A over 2. Now we've actually done all the hard work. We know that A over 2 is between pi halves and 3 pi over 4. It was in the second quadrant. So that its cosine should be, wait, which one? Cosine is plus or minus in the second quadrant. If you said positive, you are incorrect. If you said negative, it is negative in the second quadrant. And the other hard work. We also know what cosine of A is. We were given sine of A, but we used the Pythagorean identity to figure out this. Cosine of A was negative 15 over 17. So, since we've already done the hard work, we just go ahead and simplify. 17 minus 15 all over 17 over 2. We skipped some of the steps this time because we've done them so many times before. This is 2 over 17 all divided by 2. In this step, simplifying the compound fraction means taking the numerator and instead of dividing by the denominator, we're going to multiply by its reciprocal. And again, instead of multiplying top times top over bottom times bottom, you look for common factors between the top and the bottom. Negative 1 over 17 inside the square root. Much like last time, the numerator has a nice square root. The square root of 1 is just 1. So you can leave it like this, or you can rationalize the denominator. Again, that means trying to make the denominator into a rational number by multiplying the top and the bottom by the radical expression in the denominator. 1 times root 17, and root 17 times itself is just the inside. So you can leave it like this, or like this. Now for tangent. We haven't even talked about the tangent half-angle identity. Maybe you looked at it on your own. But most of the time we don't need it, because instead of doing the tangent half-angle identity, we're going to use the quotient identity. We know that tangent is sine over cosine. And that goes for tangent of A over 2 also. It's just sine of A over 2 over cosine of A over 2. Now we know what both of those things are. Sine of A over 2, cosine of A over 2. Now this is a compound fraction and we simplify it. Instead of dividing by the denominator, we're going to multiply by the reciprocal. And look at that. As long as you remember positive times negative is negative, the root 17s go away, and this is just 4. So we have a tangent half-angle identity, but most of the time we just want to use the quotient identity, sine over cosine. So for our next example, we want to find the 6 trig functions at A over 2 if we're told that tangent of A is negative 2 radical 6, and that A is in the 4th quadrant. So you know that in order to find something like sine of A over 2, we need the half-angle formula, right? So plus or minus the square root of 1 minus cosine of regular A over 2. I need cosine of A. To do cosine of A over 2, the formula was very similar. The difference was that this is a plus cosine A in here. For either of these, I need cosine of A. I don't have cosine of A. I have tangent of A. Last time, we were able to use the Pythagorean identity to get from sine A to cosine A. I can't do that with tangent. What we're going to use instead is we're going to use one of the definitions of tangent. We gave 3 definitions so far. One on the unit circle, one with right triangles, and this one. If theta is an angle in standard position, if you don't remember what that means, please look it up, and x comma y is a point on the terminal side of theta that is not the origin. We don't want x comma y to be the origin, any other point on the terminal side. Then we define the 6 trig functions as follows. Sine of theta is y over r, cosine is x over r, tangent is y over x, and in which case you need to make sure x isn't 0, where r was defined to be this distance from the point to the origin. So the picture that goes along with this definition looks like this. You've got an angle with an initial side on the positive x-axis, a vertex at 0, and a terminal side somewhere. Here's the angle theta, and over here somewhere is the point x comma y. This distance from here to here, this is r. So you've got x is this distance, and y is this distance, and r is basically the hypotenuse of this right triangle, right? So this is what we're going to use. We're going to use the fact that tangent is the ratio of y to x, and the fact that cosine is x to r. If we know the ratio of y to x, we should be able to find this. Tangent of an angle is what we said, y over x. So I want to be able to think of this negative 2 root 6 as a fraction. And anything that doesn't have an obvious denominator can have the invisible denominator 1. What do you divide negative 2 radical 6 by to get itself? 1, right? You can divide any number by 1 and get itself. So this is going to look more like this fraction. Now, is this correct? It wasn't a fraction before, so it wasn't a big deal. But we don't actually know that the numerator is negative. What we know is that the fraction is negative. And this is a big deal when we start turning this into y and x. What quadrant is this angle in? It's in the 4th quadrant, right? So we know that in the 4th quadrant, indeed the y values are negative and x is positive. So that is what we want. Numerator, numerator, denominator, denominator, and this is going to make sure, these signs, that it's in the 4th quadrant. Groovy. So what's r? R was the square root of x squared plus y squared. 1 squared is real easy, but let's talk about this for a second. If I have a product squared, and I do, you raise each factor to that power. So negative 2 squared and radical 6 squared. Negative 2 times negative 2 is 4, and radical 6 times itself, like every other radical times itself, is just the inside. So this ends up being the square root of 1 plus 24, also known as the square root of 25, which is a nice number for us. So we used the definition of tangent being y over x, and the definition of cosine as x over r, to find out what cosine is. Cosine of a as x over r is going to be x over r. And that's pretty nice. So now if I want to find sine of a over 2, I have the half angle formula. 1 minus cosine of a over 2 all under the square root. I know what this is, but I still need to figure out whether this should be the plus or minus, whether this is the positive or negative square root of all this stuff. And to do that, we needed to figure out what quadrant a over 2 was in. We know what quadrant A is in, but we haven't yet figured out what quadrant a over 2 was in. Once we figure out the quadrant, we can figure out whether sign is positive or negative there, and pick. So, if we have a bound for a, we can use algebra to turn this into a bound for a over 2. What do I have to do to turn a into a over 2? I have to divide by 2. Right? So we're just going to divide everybody in this sentence by 2. 270 divided by 2 is less than a over 2, which is less than 360 divided by 2. Simplify that, and we find that a over 2 has to be in the 2nd quadrant. Sine is positive in the 2nd quadrant, so we're going to pick the positive square root here. So let's get back to it. Sine of a over 2 is going to be the positive square root of 1 minus cosine of a. Cosine of a is 1/5, so 1 minus 1/5 all over 2 inside the square root. Getting a common denominator. 5 over 5 minus 1 over 5 over 2. Adding the two fractions with the common denominator means, well, combining. It's subtraction in this case. it means subtracting the numerators, right? If they have the same denominator, subtracting fractions means subtracting the numerator, simplifying, and now we have a compound fraction in there. So what we're going to do is we're going to, instead of dividing 4/5 by 2, we're going to multiply by the reciprocal. What's the reciprocal of 2? If you said 1/2, good for you. If you turned this into 4/10, you haven't had enough practice looking for common factors from top to bottom. We want to look for common factors and reduce them first, right? That way we don't have to make this bigger unnecessarily than we need to. 4/5 times 1/2. You have a common factor here of 2. So you're going to get the square root of 2/5. Now this is something that you could take and leave it as it is, or you could rationalize the denominator. The square root of 2 over the square root of 5. It's just going to make it easier for us to visualize when we rationalize the denominator. What does that mean? Rationalizing the denominator. It means rewriting this so that the denominator is a rational number, right? Radical 5, not rational, irrational in fact. The way we do this is by multiplying the top and the bottom by the same thing, by the radical expression in the denominator. Radical 2 times radical 5 is radical 2 times 5, and radical 5 times itself is the inside. So either this or this are acceptable here. That's sine of a over 2. Now let's try cosine of a over 2. A lot of the steps are going to be the same. Cosine of a over 2. And the first things we pay attention to are what quadrant is this in. This is still in quadrant 2, but now we're talking about cosine, so this is going to be the negative square root of 1 plus cosine of a. What was cosine of a? There it is again, 1/5. Did you see it? 1/5. So 1 plus 1/5 over 2. And we're going to take that, we're going to take 1 plus 1/5, and we're going to get a common denominator. And we're going to add the fractions. 5 plus 1 all over 5 all over 2 under the square root. So negative square root of 6 over 5 all over 2 under the square root, right? We've got, instead of dividing 6/5 by 2, we're going to multiply by the reciprocal. And again, we want to reduce before multiplying. They both have a common factor of 2, leaving you with a 3 up top. The square root of 3/5. And this is an acceptable answer, but we can see what this looks like when we rationalize the denominator. Negative root 3 over root 5. Again, rationalizing the denominator by multiplying the top and the bottom by the rational expression. Negative root 15 over 5. So that's sine and cosine. Now there's a tangent half-angle formula, but it's usually much easier to just say sine over cosine. So tangent of a over 2 is sine of a over 2 over cosine of a over 2. Sine, which was radical 2 over 5, and cosine, which was negative radical 3 over 5. And I wrote it this way because it's going to be a little easier this way. Now if you have a square root of a fraction, it's the same as the square root of the top and the square root of the bottom. So we can use that property backwards. If I have a square root on the top and the square root on the bottom, this is equal to the square root of the whole thing. So what we've got now is a giant complex fraction inside the square root. So what we're going to do is, instead of dividing 2/5 by 3/5, we're going to multiply by the reciprocal, 5/3. And we reduce before multiplying to get the square root of negative 2/3. This is the same thing that you would get if you had used this and this for sine and cosine, but this one is a little bit faster. They are the same answer. And now let's, again, rationalize the denominator just so we can see what that looks like. Negative root 2 times root 3 is negative root 6. And in the bottom, root 3 times root 3 is 3. So this is what we've got so far. We found 3 of the 6 trig functions at a over 2. We're halfway done. We need to find the other ones. Now I've written the rationalized version of each of these and the beginning version of each of these. So I can ask you, which one would you rather take the reciprocal of? I personally would like to take the reciprocals of these and then rationalize. But it doesn't really matter. So the reciprocal of radical 2/5 is going to be radical 5/2. And when you rationalize the denominator, you get radical 5 over radical 2 times radical 2 over radical 2. This is going to be radical 10 over 2. Secant since cosine was negative, this is going to also be negative. Radical 3/5, when you take the reciprocal, becomes radical 5/3. And when you rationalize the denominator, radical 5 over radical 3 times the radical expression in the denominator becomes negative radical 15 over 3. And cotangent of a over 2 is the reciprocal of this guy. The reciprocal of radical 2/3 is radical 3/2. And when you rationalize the denominator, a process that hopefully is becoming familiar, we'll get radical 3 times 2 is 6 over radical 2 times radical 2, 2. So whether you want your answers to look like this, or whether you want your answers to look like these guys, here we go. These are the values of the 6 trig functions at a over 2. So that's it. The word of the day is Rhabdodon, the rod-tooth dinosaur, and this has been a Badger Bear production.